All right, everybody, welcome to the video here for lesson number 7 on the Pythagorean identity. We are not going to do this entire lesson. I'm just going to show you kind of the key things you need to know from this lesson. So if you just kind of focus and pay attention here, we're going to kind of go through it relatively quickly. But we're just kind of seeing an idea that comes up here sometimes on the Regents exams. Something I probably wouldn't test you on, but hey, you never know. So the opening exercise tells us that the sine of theta squared can be shown with parentheses, but that's kind of a complicated notation, so we usually write it as sine squared theta. So these two things mean the same thing. So it says find the value of sine squared of theta plus cosine squared of theta for any angle. So if you take out your calculator, I know we don't really use the calculator too much in this chapter. If we were to type in the sine of 30 squared plus the cosine, type in exactly how I have it here, of 30 squared, what value do you get? I'll give you a second to try and type that in. You should get 1. The thing about this is it didn't matter what number I picked here. I could have picked 50, I could have picked 80, I could have picked 7. It wouldn't matter. It's always going to give you 1. And there's a reason why this relationship exists. And I'm going to kind of show you, and you might have even started to think about this relationship as we've been talking about the unit circle. So this is what's called the Pythagorean identity. Pythagorean theorem. We're starting to think that way. Everything we've done so far has been right triangles, so Pythagorean theorem must be somewhat involved in all of this. So if you look at this unit circle I have drawn here, we know that the distance of OQ, QP, and OP represent things. But let's first just start by looking at Pythagorean theorem basically just from that triangle. If we wanted to do Pythagorean theorem from just that triangle, I'd say the segment OQ squared plus the segment PQ squared would be equal to the segment OP squared. That's true no matter what the segment lengths are. However, because it's a unit circle, we know what these segment lengths are. OQ is the horizontal segment, so that would be cosine. PQ is the vertical segment, so that would be sine. And OP is the hypotenuse, which is the radius of the unit circle, which is 1. If we clean that up a little bit, using what we saw in the opening exercise, instead of cosine of theta squared, I write cosine squared theta, sine squared theta. We just put the little square next to the sine or cosine, telling us we're squaring that entire value. And 1 squared, and last time I checked, that's just 1. This identity works no matter what the values are for theta. So let's use this identity. We're going to skip number 2. There are other Pythagorean identities. I just care about that one. Skip number 3. Now let's go right to number 4. Numbers 2 and 3 are kind of developing these other Pythagorean identities that exist, but due to the nature of this year, I really only care that you know about this cosine squared equals 1 identity. So notice when it says use the Pythagorean identity, I have it as sine squared plus cosine squared here. It's the same thing forwards and backwards, commutative property. So it says find the value of sine given the cosine using the Pythagorean identity. So if you know cosine and you want to know sine, you can just jump right to this identity. You don't have to make any triangles. So if we know cosine, I'm going to leave sine as is, but I'm going to replace cosine with whatever the cosine value is squared. And that's equal to 1. Let's do some algebra. 3/5 squared is 9/25. If you subtract 9/25 to both sides to get sine squared by itself, you're going to get sine squared of theta is equal to 16 over 25. If you don't know where I got that from, use your calculator. 1 minus 9/5, it's going to give you a decimal. It's going to be 0.64. Hit math, enter, enter, and change it back to this magical fraction that we have of 16/25. We like fractions better here. Another little algebra trick, if we want to solve for sine, since it's squared, we're going to square root it. So we're going to get sine of theta is equal to two answers, plus or minus 4/5. The square root of 16 is 4. The square root of 25 is 5. Now we're getting two answers, but only one makes sense depending on the quadrant that we're in. This is a quadrant 4 angle. If I'm between negative 90 and positive 0, we're in quadrant 4. What do we know about sine in quadrant 4? It's negative. So we reject positive, and the only answer we care about here is negative 4 over 5. Now, you might be sitting here saying, why would we do all of this algebra if we could just make the triangles like normal? You can, right? The triangles like normal would still give you the same exact answer. This is just another method of solving it, okay? Every now and then on the Regents exam, they give you one where it tells you to use the Pythagorean identity. So this is why we're doing it, okay? Let's try B. B says find tan of x given the sine of x is equal to 12 over 13. We are in quadrant 2, so we already know tan is going to be negative. So if we know sine, that means we can find cosine. So I can say sine squared plus cosine squared equals 1. 12 squared over 13 squared is 144 over 169. If I subtract that fraction to the other side, I have no idea what that is. All right, we're going to use our calculators here, and we're going to get 25 over 169. Square root both sides, and we get the cosine of x is equal to plus or minus 5 over 13. Square root of 25 is 5, square root of 169 is 13. But since we're in quadrant 2, we know we want to reject the negative of the positive, because cosine's negative there. So we're rejecting the positive, and the cosine of x is equal to negative 5 over 13. Now from here, we can do two things to find tangent. We can make a triangle, see what the ratios are, or we can divide, because we remember tangent is equal to sine over cosine. So the tangent of x is equal to the sine value, which we said was 12 over 13, over the cosine value, negative 5 over 13. Since they're both over 13, they cancel, so we're left with negative 12 over 5. Right, these 13s cancel since they're the same on top and bottom. Now, the real reason why we like this idea of this sine squared plus cosine squared equals 1 is for these nasty ones with decimals. Yes, you can change 0.75 to the fraction 3/4 and make your triangles that way. That works too. Or you can do this process. So since we know the sine value, we're going to take the sine value and square it. Add it to the cosine value. I then know that 0.75 squared, whatever that comes out to be, 0.75 squared is 0.5625. If I move that to the other side, it's just algebra. That's all we're really doing here today. Whatever that comes out to be. 0.4375. Square root it. Remember, two answers here. We get 0.661 dot, dot, dot. Some crazy fraction or decimal. Now, since we are in quadrant 3, I know I want the negative answer, so we're going to reject the positive, and we want negative 0.661 dot, dot, dot. Now, it wants secant. It doesn't want cosine. So to find secant, we're going to say it's negative 1 over this nasty decimal that's still in our calculator. And if we approximate that to the nearest hundredth, like it says, I'm going to do 1 divided by that answer in my calculator. Don't round it. And we get 1.51. Not 0. 1.51. That's my answer for secant using this method. That's it. That's all we need to be able to do from this Pythagorean identity lesson. All right. If you have questions, reach out to me. All right. If not, I will see you all soon.